are familiar with how to predict the pH of a variety of different scenarios. For example, if we put a strong acid in solution and we're asked the pH of that solution, like what is the pH of a 0.01 molar HNO3 solution? Well, if we're asked that question, we should be able to answer it because we know what to do when we are faced with a solution that is a strong acid, right? Because it's a strong acid, that means it will completely dissociate, resulting in 0.1 molar of the hydrogen ion and 0.1 molar of the nitrate. And pH is related to the hydrogen ion concentration. Therefore, the negative log of the hydrogen ion concentration would be the pH for that scenario. In the solution of a strong base, so for example, what's the pH of a 0.002 molar solution of magnesium hydroxide? All right. In this scenario, we have a strong base here. We know that when this goes into solution, it's going to completely deionize or dissociate, and our concentration of hydroxide ion will be not 0.02 because there's two of them, but 0.04, right, molar. And 0.04 molar hydroxide ion, we take the negative log of that value. That'll be the pOH. 14 minus the pOH will give us the pH. Okay? Strong acid, strong base, right? If we're given a concentration of a weak acid, for example, what's the pH of a 0.01 molar solution of HCN? Okay? We can identify the hydrogen ion concentration, which is how we take identify the pH, right? As soon as we find the hydrogen ion concentration, we can take the negative log of that, and that'll be our pH. But HCN's concentration is not the hydrogen ion concentration because HCN is not a strong acid, it's a weak acid. Therefore, to answer this question, we need to have a K associated with that HCN, which indicates to us how much of the HCN will actually dissociate into the respective ions, correct? And once we have that, we can do an ice table, identify the equilibrium concentration of the hydrogen ion, and then take the negative log of that, and that will be the pH for our solution. All right. We also have a very similar way. What's the pH of a 0.01 molar solution of ammonia, for example? Ammonia. Well, we can think of this hydrogen ion here. Sorry, this base. Ammonia is a base, and we'll generally have a clue about whether that's an acid or a base because a K will be provided. And in this case, they will be needing to provide the Kb for us because NH3 will act as, whoops, that needs to be water here, H2O, will act as a base reversibly, right? Whoops, there we go. And the result here will be the NH4 plus, which is the conjugate acid of that base, and the hydroxide ion. We can use an ice table again. Initial concentration, 0.1 molar, change, equilibrium, set that equal to the Kb. Will have to be given a numerical value there. And then the equilibrium concentration of the hydroxide ion, negative log of that will be the pOH. 14 minus that would be the pH. Okay? Excellent. So, those are all in previous videos, and you want to be experts at that, at all those scenarios. Here's another scenario that you want to be an expert in, okay? And that is when you add a salt to a solution. You know, that's not an acid, not a base. At least we've never talked about salts being acids and bases, but they can be. I mean, this isn't terribly surprising. Magnesium hydroxide is a salt, right? So you add it to solution and it can change the pH, clearly. But what we're talking about is the addition of salts like sodium carbonate. Whoops, CO3. Sodium carbonate. If you have sodium carbonate, Na2CO3, let me rewrite that. That does not look good. Na2CO3. There we go. If you have sodium carbonate, you know, if you remember from our lab experience, we realized or learned that it makes the solution basic. So what's going on there? Well, this dissociates Na, two of them, CO3 with 2- charge, right? And if any of the dissociative products of a salt, all right, are the conjugate base of a weak acid, right? If we know it's the conjugate base of a weak acid, that means it's a fairly good base. Remember that? Strong acid, its conjugate base is not a good base, and that's why its acid is strong. But for this anion, its acid is weak. Therefore, that tells us that if it ever has the opportunity to interact with water and remove a proton, it will do that and form the bicarbonate ion and the hydroxide ion. Showing us that, now this is at equilibrium, there's going to be an equilibrium there, but qualitatively, meaning will the pH rise or lower upon the addition of this salt, the pH will go high, right? Because we're making the solution basic. If we knew the Ka for this, and this would really be a Kb, sorry, if we knew the K for this equilibrium, where the carbonate ion is acting as a base, we could predict the hydroxide ion concentration and know the pH of the resultant solution. Okay? So, adding to our list of solutions that we could identify the pH of, right? We're adding a scenario where we can qualitatively, or in other words, look at a salt and say, wow, you put that into water and it will make the solution basic. Or you put that into water and it will make the solution acidic. Or you can put it into water and it will not change the pH of the solution at all. Okay? And the way that we do this is we look at the compound. So HCl, if we put that into solution, make a 0.1 molar solution of it, we know it's going to make the solution acidic because HCl is a strong acid. Now NaCl, sodium chloride. Well, when we put sodium chloride into solution, what is going to be the result? What are the resulting ions, Camille? If I put sodium chloride into water, make a solution of sodium chloride, what are the resulting ions that I'm going to have in solution? Are you there? I can't hear you, Camille. Alyssa, do you want to help her out? She's probably got some microphone problems. Or maybe my volume's not up. I think my volume's okay. Alyssa, are you there?
Me and Alyssa are together.
Okay, so, great. Go for it, Camille.
We're going to go working, sorry. You know, I really don't know. I first said neutralize.
Okay, so...
Negative ion.
All right, so when I put sodium chloride, this salt right here, into solution, what ions am I going to get? That's the first question. What ions am I going to get? I'm going to get...
Na plus, Cl minus.
That's right. Those are the two ions that I'm going to get. And then we just have to look at those ions and try to decide if they are going to influence the pH of the solution. Well, how would they influence the pH of the solution? For example, if I had the negative chloride ion, what do you think, Camille?
Well, I'm going to say that it's going to react with the water.
All right, that's right. If the chloride ion can react with the water and negative charge looks like it's probably going to pull that hydrogen off, what would be the products?
NaCl2?
Well, it's just this little bottom part here, this little direction here. So the hydrogen ion is going to go with the chlorine, and HCl is our product, and the rest is going to be the rest of that water molecule left over, which is the hydroxide ion. Okay? Now, this isn't actually what's going to happen. This is just theoretically what this ion could do in solution. it could turn the solution basic if this chloride ion was the conjugate base of a weak acid. But we can see that it's not the conjugate base of a weak acid. It's the conjugate base of what kind of acid, Alyssa?
I'm sorry, can you say that again?
The chloride ion, we can see, is not the conjugate base of a weak acid. If it's the conjugate base of a weak acid, it wants to pull a hydrogen off and make its conjugate base. But chloride ion is the conjugate base of what kind of an acid?
A strong acid?
A strong acid. And strong acids aren't going to form in solution. There's not going to be any HCl in solution. So this will not occur heading to the right. So chloride ion will not influence the pH of the solution. Now, sodium ion. Yeah,
Sorry.
Go ahead.
Couldn't it be an intermediate and then react farther?
HCl here, you mean?
Yes, sir.
Well, if there was any significant amount of this in solution, then possibly. But this, it won't have any significant amount of it because the Ka for the chloride ion and the hydrogen ion is so large, right? Or in other words, HCl dissociating into H plus and Cl minus. The K value there is so large that there's essentially no backward reaction occurring. Okay, good question. So now let's look at what the rest of this salt might do, the sodium ion. Sodium ion, what could a positively charged ion do in solution? Well, if it's going to interact with water and do something, it would have to attract the hydroxide ion away from water. And if it did that, it would make sodium hydroxide and leave behind the hydrogen ion. So we ask ourselves, well, is that going to happen? Are we going to get any sodium hydroxide resulting in solution from when we add the sodium ion? How do we know that this is not going to happen, Brielle? How do we know that the sodium ion is not going to remove a hydroxide ion and form any significant amount of sodium hydroxide?
Is it because it's positive? I don't know.
It's because this sodium hydroxide, what kind of a compound is that? Do you know? What is sodium hydroxide? Is it an acid? Is it a base?
I don't know.
It's a base. It's a base because if you take sodium hydroxide and put it into water, it completely dissociates into sodium and hydroxide ion. So because we know that sodium hydroxide is a strong base, we also know that sodium ion, another way of saying that is any salt that contains sodium always dissociates in water, right? So when you put sodium ion in solution, it will never interact with water and affect the pH anyway because it can't pull hydrogens, it can't pull hydroxide ions away from water and result in the hydrogen. So what that tells us is that neither the sodium of sodium chloride or the chloride ion of sodium chloride are going to influence the pH. Neither of these will occur. All right, so that means that this is not going to affect the pH of a solution. It's going to remain neutral. Now, sodium cyanide, or the cyanate ion, all right? So, we have to do the same thing. We have to look at this salt. It's not a strong acid. It's not a strong base. It's just a salt, sodium cyanide. But we have to answer some questions about, will a solution of sodium cyanide be neutral or acidic or basic? Okay? So the way we do this, again, is we identified the ions that will result when you put this into solution. Sarah, what ions will result when I put sodium cyanate into solution?
Would it just be sodium and cyanate?
That's right. Very good. Those are the ions. Now, we want to look at these ions and see if somehow they'll affect the pH of the solution. Do you think the sodium ion will affect the pH of the solution, Sarah?
No.
How do you know?
Like we just talked about, sodium completely dissociates in water, so there'll be
none of this happening.
Yeah.
Right, very good. So I could redraw it and think about what sodium's going to do, but we just did that, so hopefully it's okay if I skip that step and say the sodium ion is not going to influence the pH. But the Cn minus ion, Sarah, what do we know about Cn minus? Is it the conjugate base of a weak acid?
Yes, I think so.
It is the conjugate base of a weak acid. So if it's interacting with hydrogen ions in water, or hydrogen from water, what will it do? Because this is the conjugate base of a weak acid, what will happen here?
So it should react with the water and form HCN plus OH.
That's right, the hydroxide ion. And if we didn't know that, we could just write that and say, And then if we saw that this was, ta-da, it is a weak acid, then we'll remember, oh yes, that's the conjugate base of a weak acid. Therefore, if you put cyanide ion into solution, it's going to take that hydrogen. Because it's the conjugate base of a weak acid, it's a fairly good base. It's going to take that hydrogen ion, and it's going to release the hydroxide ion. Therefore, how will the pH change if I put sodium cyanide into solution, Sarah?
So it will make it more basic.
It'll make it basic. That's right. Sodium cyanide behaves as a base. Okay, very good. So this one's for you, Camille. We have HCN, and we're going to put it into solution. Okay. Any ideas, Camille? Oh, Camille's not answering questions right now. Sorry, Alyssa. Here's one for you, Alyssa. We're putting HCN into solution. If I have, or what kind of compound is HCN, Alyssa? Any ideas?
I can't remember. I don't know what type of compound it is, but I think I know how it's going to react.
What's it going to do? What do you think it's going to do?
They'll dissociate to H positive and Cn negative.
Okay. So does that tell us any information about how it's going to affect the pH?
Yes, sir. I think it'll remain neutral because both of them will be reacting at the same rate.
Well, what if this K was 100? What would that tell us?
It means that there are a lot more products than reactants.
That's right. And if one of our products is an H plus ion, then what would that tell us about the pH?
That it's going down.
Yes, that it'll be acidic, right? So we don't know what the K is, but because we put HCN in solution, and by the way, what is HCN? HCN is a weak acid. So, and how can we know that? We just know it's not on the list of strong acids, and it starts with a hydrogen ion. Therefore, this, when we put this into solution, it will make the solution acidic. How acidic? Well, we could answer that if you told me the K value. If I knew the K value, I could know how much dissociation was going to occur, identify the X in my icebox, right? Identify the resulting equilibrium concentration of the hydrogen ion, take the negative log of that, and that would be the pH of that solution. But just qualitatively, I'm going to know that that is going to make an acidic solution because HCN is a weak acid. All right.
I have a question.
Yeah, go ahead.
So, in the one before, the Cn created a reaction that, constituted a base. And I know it was from the beginning, but I'm just confused why that didn't happen here.
Well, before we were putting sodium cyanide in the solution, and we had a sodium ion and the cyanide ion. And so we said, okay, is sodium ion going to react with water to form the hydroxide ion and sodium hydroxide? Right? That's what the question, these are the two questions we'd have to answer because of the resulting ions from that salt. And we said, no, that's not going to happen because sodium hydroxide is a strong base, therefore it's never going to form. But this, if you have the cyanide ion floating around, the first thing it's going to do is remove a hydrogen and form HCN. Because this is a weak acid, or a conjugate base of a weak acid. This is a weak acid. This is the conjugate base of a weak acid. So when you put this into solution, this is what's going to result because that's stable. All right? If you put this into solution to start off with, then it's more stable than the products, telling us that the K is actually, for this, probably like 1 times 10 to the minus 7 or something like that. I don't know exactly what it is. We could look it up, right? But because there will be some hydrogen ion, as opposed to just basic neutral solution of water, then this will result in an acidic solution. It might be only slightly acidic, like 5.3 or something like that, but it will be acidic compared to the neutral water. Does that make sense, Alyssa?
I think so. So because the bond, it will go back, it doesn't bond or react again with H2O.
That's right. This thing, well, you know, it will. It'll take a hydrogen off of water, right? But
would be going back to the HCN original.
It would be going back to the HCN original, and this H plus would go bond with the resulting hydroxide ion that is formed, right? So at pH 7, there is 1 times 10 to the minus 7 molar hydroxide ion and hydrogen ion always around. So as soon as there's any free hydrogen ion in excess, it will, if there's any of this in excess, it would find any hydroxide ions it could. So the cyanide ion here, even if it pulls a hydrogen from a different water molecule and resulting in a hydroxide ion, this will combine with a different hydroxide ion. So in general, the specifics of how that occurs is nice to understand, that it can go to any water molecule anywhere, but this is what's the kind of the nuts and bolts of what's happening when we put HCN into solution. So we've talked about a strong acid, talked about a salt, a neutral salt. We've talked about a salt that would make the solution basic, and now here a weak acid, which is going to make the solution acidic. What is going on here? Na2S. Na2S. Well, whose turn is it? Brielle, I think it's your turn. What kind of ions do we have to worry about to determine whether or not they're going to make this solution acidic or basic? What are our two ions?
Sodium and ion.
All right, the sodium and the sulfide ion, S2 minus. Okay. All right. Now, do you think that sodium is going to alter the pH somehow?
No, sodium's not going to affect.
That's right. We just went over that a couple times, and if you forgot, you're watching the video and you forgot, you can go back and take a look, understanding that. Because it's worth drawing out again over and over and over, but only kind of. So, what about S2 minus? Do you think it's going to influence the pH at all? Or let's just draw how it might. How would we draw how it might? S2 minus plus what?
So you'd add water to it.
Mm-hmm.
And it would go to HS minus and then an OH minus ion.
Okay, very good. Whoops. So, there we go. I don't know. Is HS minus, or even you could take the HS minus here and combine it with another water molecule and form H2S. Right? Are either of these weak bases? H2S? Or sorry, not weak bases, weak acids. Are either of these weak acids?
I don't think so.
Well, what kind of acid is H2S? Is it a strong acid or a weak acid?
It would be weak because it's not on a strong acid list. So I guess it would be
Yeah,
a weak.
good. It is. These both act as can be weak acids. Weak acids. So when you put the sulfide ion in solution, because it is the conjugate base of a weak acid, and it results in another conjugate base of another weak acid, that means that the sulfide ion is going to make the solution what? Acidic or basic, Brielle?
Acidic.
Well, what's left over here?
Oh, OH minus.
Yeah.
So basic.
So basic. That's right. So the presence of the sulfide ion pulls protons off of water and results in hydroxide ions, making the solution basic. And the simple and easy way to say that is you add sodium sulfide to solution. The sulfide ion is the conjugate base of a weak acid. Therefore, it will make the solution basic. Okay. Alyssa, how about this one? Na3PO4. Na3PO4. Is that going to make a solution acidic, or is it going to make a solution basic, or is it going to be neutral when I put it into water?
Well, the PO4 has a -3 charge, so it'll go to Na plus and PO minus 3, and we already know what happens to Na.
Okay.
So if you read, PO4 to H2O, I guess it would be, I don't really know how that would react.
Okay. Well, we got a +3 charge here, right?
Mm-hmm.
What am I doing? Not +3, -3. -3 charge there, right?
Mm-hmm.
So
the oxygen has -12 altogether, or 12, or 4 times 2, sorry, 8 negative electrons, so the P has to have 5 positive.
okay. In terms of the oxidation number, very good. Now, the hydrogen ion, sorry, the phosphate ion here, what we want to ask ourselves is, and this is what we're always asking, is that the conjugate base of a weak acid?
I don't think so.
Now, what we can do to answer that question is add as many hydrogens as necessary and see if it looks like an acid that we're familiar with. So how many hydrogens would we add here?
H3
3.
PO4.
So H3PO4.
So I'm sorry. Whenever you have a compound that you're reacting, you don't split it up. If it's in a polyatomic ion, you keep it together.
That's right. Polyatomic ions are going to stay together in solution.
Okay, that makes sense.
Unless there's a redox reaction, but here we're just putting these salts into solution, and the resulting ions are going to be the sodium ion and the phosphate ion.
Okay, thank you.
So then we're going to result in if we look at this, we see that that's the conjugate base for this acid. And now we say, is that a strong acid or a weak acid? Or, yeah, it's got to be one of them, right?
I think it's a weak acid.
It is a weak acid. So what would that mean? That would mean that if
it doesn't affect.
It does what?
It affects the pH.
It does. That's right. H3PO4 plus 3 hydroxide ions. 3 water molecules are required for this. All right. How is it going to change the pH? Make it acidic or basic?
Basic.
Basic. Very good. And what we say, simply, the phosphate ion is the conjugate base of a weak acid. Therefore, putting sodium phosphate in solution will make the solution basic, because the phosphate acts as a base, right? Okay. Here we go. Ammonium chloride, ammonium chloride, NH4Cl. Brielle, can you, let's see, who is it? Yeah, Brielle, can you help me with the ions that will result when we put ammonium chloride into solution? What will we get?
So will the NH4 stay together, or will they split?
It will stay together. It's just an
Okay.
ion in solution. So we get,
And then,
what else?
and then the chloride ion.
Okay, very good. Now, will either of these affect the pH?
We know that the chloride ion is not going to.
Okay, let me write that one out because it's been a while. But if this were to interact with water, we would be asking, this negative charge would be trying to pull a hydrogen off and create HCl. And why won't that reaction ever go to the right, Brielle?
Because the HCl is like a strong acid.
That's correct.
So it's not going to react that way.
It's never going to be together like that. Very good. So this is not going to occur, and telling us that the chloride ion is not going to influence the pH of this of this solution. Now, NH4 plus. Okay. What might it do with? Well, I don't know. What might it do with? We could draw water in here if we didn't know what else to do.
Let's go to NH5 plus.
Okay.
And then OH minus.
That's a possibility. NH5, whoops, plus and OH minus. Okay, what about this though? Could it do this? NH4 plus dissociating into NH3 and H plus?
I think so.
Yeah, because this here is a weak base. A weak base. Therefore, its conjugate acid is a fairly good acid, right? So now we might not know anything about NH5 plus, and that's because it's not let's see, here NH4 plus is not an acid. NH5 plus is not an acid. All right. But hopefully when we do this reaction here and see NH4 plus dissociating into H plus and ammonia, we realize that this is a weak base. Now again, if this is a weak base, Brielle, what does it make this compound over here?
A stronger acid.
That's right. Very good. Not a strong acid, right? But a stronger acid. Very good. So, having NH4 in solution, NH4 plus in solution, it will influence the pH by making it acidic. That H plus will result in the solution being acidic. Okay. Now that was a lot of practice, but it might not have been enough. We have to be able to get good at being given any old compound, right? Oops, there it is, KHCO3. Another example, we put this into solution. Will the resulting solution be acidic or basic or neutral? We have to break it up into ions and then think about how those ions might interact with solution. If I were to think of potassium interacting with water, positive charge, taking a hydroxide ion to form KOH and H plus. And then I'll remember, oh no, KOH, that's a potassium. Anything that has potassium is always soluble. This is a strong base. So the potassium ion is not going to take that hydroxide ion and form a potassium hydroxide because this is a strong base, therefore that's a weak acid. HCO3 minus is negative charge there, is that going to pull a proton off of water? I can draw the product H2CO3 and hydroxide ion. All right. Take a look at this for a second. Oh, H2CO3. Yeah, that's a weak base. Sorry, a weak acid. That means that that is a fairly strong base. And so this is going to occur, and you're going to get some hydroxide ion. Putting this into solution will make it basic. Okay? So we've got to have some practice to get used to answering those types of questions. Another just a quick example here. If I have rubidium nitrate, take our ions, NO3 minus, rubidium ion, you can combine it with water, positive charge, therefore theoretically it might take a hydroxide ion and form rubidium hydroxide and the hydrogen ion. All right, but looking at our solubility rules, this is group 1 again, therefore this is not going to happen. The nitrate ion, NO3 minus, if I were to give that a hydrogen, it would be HNO3, right? That's a familiar acid. H2O and OH minus. Things look familiar there. Sarah, what do you think? Is that going to, if I put the nitrate ion in solution in the form of rubidium nitrate, is it going to make the solution basic?
I think it will because HNO3 is a weak acid.
HNO3?
Or is it a strong acid?
It's a strong acid.
Okay.
Strong acid. So what does that tell us?
So that means that
Not,
it won't happen.
not going to happen,
Yeah.
will it? Because the strong acid won't come together. Therefore, a compound like rubidium nitrate, how would it affect the pH? It would just, it wouldn't. It would be neutral, right? Okay. Now, that's our qualitative portion. And now we get into our quantitative, where we actually can know what the pH is of a solution, for example, of 0.1 molar sodium fluoride. 0.1 molar sodium fluoride. We do the same thing with the sodium and the fluoride, and we recognize that the fluoride ion is the conjugate base of a weak acid, HF. Therefore, fluoride ion, HF, has we can identify what its Ka is. We can look at fluoride ion behaving as a base, right? And the Kb, so if we knew the Ka for HF, then the Kb for the conjugate base of HF, which is F minus, would be this relationship, right? Ka times Kb equals Kw, or Kw divided by Ka equals Kb. And then initial concentration, 0.1, 0 and 0, minus x, x and x. And again, we knew it had to shift to the right, decreasing our reactants, increasing our products because we didn't start with any products. Equilibrium concentrations, set this up in an equilibrium statement and set it equal to the Kb, because this is the fluoride ion acting as a base, 1.47 times 10 to the minus 11, solving for x, taking the negative log of that, right? Negative log of the hydroxide ion concentration is our POH, 14 minus that will be our pH. So if you put a 0.1 molar solution of sodium fluoride in solution, or you make a solution of 0.1 molar sodium fluoride, it will have a pH of 8.08. Okay, let's try another one just like this. Okay, so if I have if I have a solution, I make a solution of NaHCO3, 0.1 molar NaH. Oh, that's not what I want to do. Let's try that again. 0.1 molar solution of potassium cyanide. What will the pH be? All right. If I know that HCN Ka is equal to 1.3 times 10 to the minus 7. Okay, so what's the pH of a 0.1 molar solution of KCN if I know that the HCN's Ka is 1.3 times 10 to the minus 7? All right, Alyssa, you think you can help me solve this problem right here? We have this little pattern up here on the left that we can use to help us.
I can try.
Okay.
So first we have this KCN, and it reacts with H2O. Should we do the reaction first, or should we?
Sure, that's fine. Which one are we going to be concerned about? Which ion?
The K ion.
The potassium ion? How is it going to react? What's it going to do? K plus
H2O, and then it'll go to AOH plus H positive, but that's completely soluble.
Okay. So that one's not going to be the one we're concerned about. Is it?
We have this N negative,
Okay.
and we combine that with the H2O, and that becomes HCN, which is a weak acid, so that will cause the solution to be basic, right?
Yeah, that's right. Okay, now do I know the K for this? I'm going to need to know the K if I want to know the hydroxide ion concentration to find the pH. Do I know the K for this reaction?
Isn't it the inverse of the Ka of HCN?
Okay, it's not the inverse, but it is derived from this. It's derived from this relationship, which we'll write up here. Kw is equal to Ka times Kb for that acid's conjugate base.
Mm-hmm.
So, do you remember what Kw is?
1 times 10 to the negative 14.
Good. And the Ka is our 1.3 times 10 to the minus 7. So therefore, our Kb (1 times 10 to the minus 14 divided by 1.3 times 10 to the minus 7). 7.69 times 10 to the minus 8.
So would that be the Kb as well for that equation, since the Cn negative is the same?
That's right. Here, this Kb derived this way by taking the relationship between Kw and the Ka for its conjugate acid is the equilibrium constant for that its conjugate base pulling protons from water, acting like a base. Okay, so 7.69 times 10 to the minus 8. Am I closer to the pH? What do I do now?
We could find the pOH using that number.
Okay.
Being the negative log of 7.69 times 10 to the 8.
Okay, I don't think I need to take the negative log of that quite yet. First, I need to finish up my ice table, right? What was my initial concentration of cyanide ion? Anybody, any ideas?
1 molar.
Yeah, the 0.1 molar, right? 0.1. And then my initial concentrations of these were 0. And then the change is going to be what here?
Minus x.
Very
plus
good.
F.
Very good.
So the x squared over
That's right.
0.
So this Kb is equal to products over reactants, liquid there, not going to be involved, right? So x squared over 0.1 equals 7.69 times 10 to the minus 8. And then we can solve for x. So I got 7.69 times 10 to the minus 8 times 0.1. What's next? Times 0.1. And then the square root of that value. So 8.77 times 10 to the minus 5.
That would be the concentration of the OH and the C, or the HCN, correct?
That's right. So how does that get me closer to the pH?
So we can use that to find the OH, or I guess the pH as well, since it's the same concentration.
Well, it's the concentration of hydroxide ion, right? So how do I find the pH if I know the concentration of the hydroxide ion?
We can do the POH equals negative log of the 8.77 times 10 to the 5th.
Very good. That's our 4.05 is our P what?
Our POH.
That's right. And then how do I get to the pH?
14 minus 4.05.
Very good. So the pH is 9.94. 9.94. Now, is that acidic or basic, that 9.94?
That is basic.
That's right. And is that what we said would happen if we put KCN into solution?
Yes, sir.
Yeah, that's right. Very good. Cyanide ion would interact with water and make the solution basic. Okay, very good. So we've increased our abilities. We got the ability to do all sorts of stuff now, right? We can identify the concentration of a strong acid. We can identify the concentration of a strong base, or the pH of a solution of strong acid. We can identify the pH of given concentration of strong base, pH for weak acid, pH for compound behaving as a weak base, and now two problems that we just did, identifying the pH for a salt that's going to influence the pH of the solution. Okay, so we've joked a little bit about the quadratic equation because it's a funny equation, right? But, you know, it's a mighty fine tool if you ever need to use it, remember it, pull it off of Google, whatever it takes. We would need it to answer some questions if we didn't have our solver, and if we couldn't simplify, right? We couldn't simplify. I don't think we'll find ourselves in that sort of situation on any of our exam questions. But it is a healthy, our discussion that we're going to have about this here is healthy for a different reason. Let's just look at this sort of a problem here. Here's a solution, or situation where we get down to x squared. All right, hopefully everybody can follow how we are solving this problem. We're trying to identify the pH of a 0.1 molar solution of this material. HSO4 minus combines with water and will give up a proton and result in the SO4 2 minus ion, because HSO4 minus is an acid, and they told us right there if we were to forget. But the Ka here, 1.1 times 10 to the minus 2, that's essentially 0.011, is very close to the concentration, 0.1. So it's not far enough away to just drop our x here, right? And so when we get our x squared over our equilibrium concentration of the HSO4 minus, 0.1 minus x, and set it equal to this here, we get a mess, and then that's where the quadratic equation can come in handy, and we can solve the problem. Just have to click a couple more things down and we're done, right? But in reality, this becomes a headache because of having to kind of use this whole quadratic equation. Even if you know it, it can become cumbersome. So we're going to introduce an additional way to solve this sort of problem. And this is it. We come to this point right here where we would normally not feel comfortable getting rid of the x. Now, Sarah, can you tell us why we decided we couldn't get rid of the x in this scenario?
Is that because Ka is not very small?
That's right. It's too close to the concentration of the initial material that we have. And so 0.1 minus x would not be an insignificant change. Therefore, we can't just drop that x. But what we can do is, if we drop the x in the binomial, even though we shouldn't drop it, solve the problem and get an answer for x, 0.032, all right, we can kind of know that this 0.032 will not be correct because of the Ka having so close to the initial concentration. However, what we can do is we can just take that 0.032 and substitute it in for this x that we didn't feel comfortable dropping. So if I take 0.032 now and substitute it in for that x, and then solve it again, I get this time 0.026. Now, if I take this 0.026, again, it might not be the right answer, I still don't know, but then I put it in again here and solve the problem the second time, or third time, depending on your perspective, I get 0.027. Then I can take that 0.027, put it in it again, and this time I get 0.027 again. So what that has shown me is that essentially I've substituted in the x's that I get that I knew were incorrect and gradually found myself the actual correct answer. Okay? So this is a method that can be quicker for solving these types of problems. So if you're ever concerned about it, you can just not drop the x. Sorry, you can drop the x to start off with. Whatever x you get, start over with that x and substitute it into here and solve for these upper x's. And you can get a new answer and keep doing that until your answer stops changing. And that will be the resulting correct answer. Okay. It's a really cool tool. We're probably not going to be using it anytime soon, but it shows you that there's a lot of power that you can get from approximations. All right. Let's think about a titration here for a second. To introduce the next concept of buffers, we want to talk about how a titration occurs. In a titration, and specifically in this titration, I have an acid. This is acetic acid. Okay, so I have an acid in my Erlenmeyer flask where I'm going to perform a titration. And I have a burette. Okay, and in the burette, I'm going to add, I have some base, and I'm going to add drop by drop base into my acid. And then as the titration proceeds, there's a curve that's going to result if I were to plot pH versus the amount of base, OH minus, that I've added to the titration. And this curve is monitoring the pH of this solution as the base is added. So it starts off acidic, low, and as I add base, we might expect the hydrogen ion concentration to go up. Sorry, the hydrogen ion concentration to go down and the pH to go up. Because again, I'm adding base, hydroxide ion. Each drop of hydroxide ion that I add consumes a hydrogen ion, reducing the number of hydrogen ions, reducing increasing the amount of hydroxide ion, increasing the pH, right? But the slope of this line is not linear because pH is not a linear relationship, right? It's a logarithmic relationship. pH is the negative log of the hydrogen ion concentration. So as I add hydroxide ion base, right? So here's an example of adding some base. The hydroxide ion removes the hydrogen ion from my solution. And once that hydrogen ion is converted into water, then more of this acid, this weak acid, will be free to dissociate. I'll get more acid dissociated and more of the dissociated ion here, which is called the acetate ion or the conjugate base. And that's what's going to happen every time I add hydroxide ion, right? The resulting lack of hydrogen ion will result in more dissociation and more acetate ion. So, as I continue to add hydroxide ion, this occurs over and over and over again, and my pH only changes relatively slightly. And the reason why it doesn't change very much is because as I'm adding hydroxide ion little by little, it's being consumed by the excess acid that I have. And if we look at my pH curve, it just kind of goes along, right? And it keeps doing that every time I add a base because there's plenty of acid to be consumed. Now let's think about what would happen if I added some more acid at this point. I know that if I add more base, it consumes an acid molecule, shifts over here, and the pH only changes a little bit. If I add a molecule of acid, H plus ion or H3O plus, what that will do is it will just interact with one of these acetate ions, and that acetate ion will become acetic acid. So because I have this acetate ion floating around, this is the conjugate base of a weak acid, waiting to take hydrogen ions if they're added, then I find myself in a situation with some weak acid and its conjugate base. I find myself in a situation that if I add base, this is consumed, but the pH doesn't change very much. If I add acid, its conjugate base over here is consumed, but the pH still doesn't change very much. And we call this a buffer. So right now we have the solution in a buffer situation because we have some acid here available to donate hydrogen to any base that I add, and I have some conjugate base over here ready to donate or consume any hydrogen acid that I might add. All right, so that's a buffer, a solution of an acid and its conjugate base that will maintain the pH. If I keep adding base, then eventually I'll get down to my last molecule of acetic acid. It will dissociate, and when that occurs, my next addition of base will change the pH drastically. It'll pass through neutral, and then my next hydroxide ion will change the pH even more drastically there, and we'll get what we call a sigmoidal curve, or a sharp change where we've run out of our acid. Okay, this titration curve here represents again the initial concentration of acid, and then the consumption of the acid, conversion, all of it to its conjugate base. Right here is when we just barely ran out of our last bit of acid. Over here, all of our material is conjugate base. Over here to start with, it's mostly acid, a little tiny bit of dissociated conjugate base based on the Ka. And right in between here, we call our buffer region, our buffer zone. Because when you're right here, you still have some of the acid and you still have plenty of the conjugate base, and so you create a buffer. You create a buffer again when you have a weak acid and its conjugate base, because the weak acid behaves as an acid and its conjugate base can behave as a base. So you have a buffer. And this in here, halfway between the beginning of a titration and the end point, is the strongest buffer zone. All right, so we can identify what the pH is of a buffer made by combining 0.1 molar acetic acid and 0.2 molar acetate ion. See how we added the acetate ion? In the form of sodium acetate. The sodium doesn't contribute to the pH. The acetate ion is the conjugate base of a weak acid, so it's going to try to influence the pH. And we can find the pH of this solution by looking at our initial concentrations, 0.1, 0.2, right? And now the change. Well, now we don't have nothing over here of this acetate ion, so we might have to look at the Q. However, we do not have anything in terms of H3O plus ion, or acid. So because there's still nothing here, this is going to be negative X, and these are going to be positive X's. All right, and then the equilibrium concentration, 0.1 minus X. This is our Ka, 1.8 times 10 to the minus 5, so we can drop that X. These are X and X. Oh, this is, sorry, 0.2 plus the X, but again, very small compared to the Ka. Therefore, we can identify the X, which is our hydrogen ion concentration, simply by using the equilibrium concentrations of our products over the equilibrium concentration of our acid and setting that equal to the Ka. X will equal 9 times 10 to the minus 6. And then what do you think, Alyssa? What do we have to do with that X to find the pH?
We can take the negative log of the X.
That's right.
Find the pH.
That's right. Negative log of that X will give us the pH. So we've identified the pH of a buffer using an ice table. We had initial concentrations not just of one, but of two components. Because this was 0, again, we still knew that we shifted to the right. Now, if I look at the general dissociation of any acid, here it is, HA, water, H3O, A minus. The general dissociation of any acid is going to have a K value equal to this statement here. And if I take the log of all of these statements, log of both sides of the equation to start off with, it'd be the log of the left equaling the log of the right. And I can rearrange this, right? This is a quotient here. So if I take the log of the H3O plus out, which is convenient because we said that the log of H3O, well, the negative log of H3O plus is the pH. So that's kind of interesting. So what I have here is the log of Ka plus the positive log of H3O plus the log of A minus over HA. But I can change those signs and make this negative log of H3O plus equaling negative log of Ka plus the log, whoops, this is supposed to be a minus sign here, minus the log of A minus over HA. And then the negative, oh, no, that's right. I switched. I brought this over here and brought that over there. That's why they became negative. This stays positive. And then negative log of H3O plus, that is the pH. The negative log of Ka, that, again, the negative log just takes the P, gives us this value called pKa. pKa. We'll talk about what pKa means. But we have a new equation here called the Henderson-Hasselbalch equation, where we can identify the pH of a solution if I know the pKa of the acid that I'm dissolving in that solution, and I know the concentration of its conjugate base. So if I have the concentration of the conjugate base, that's A minus, HA is the concentration of the acid, and that quotient there, taking the log of that quotient, adding it to the pKa, will give me the pH of the solution. Now I'm going to tell you what the pKa for a solution is, for a compound is. The pKa is a special pH. It's a special pH. It's the pH that results when you have, for any acid, all right, exactly 50% of the acid associated and 50% dissociated. So here's a compound, an acid. It dissociates H plus into A minus. All right. Based on the Ka, some will dissociate and some won't. But if you adjust the solution to this acid's pKa, the pKa is a special pH. It's a pH that will exist when you have exactly half of this material dissociated. So when you have 50% of your material in the form of HA and 50% in the form of H plus and A minus, then you'll be at that special pH. For a titration curve, the pH versus, again, adding base, the titration curve will look like this, right? And we'll have this region right here, which we called the buffer zone, right? And when we're exactly right between there and there, right, when we're right between those two, we'll be at what we call the pKa, or the special pH in which half of our acid has been dissociated. This would be 100% dissociated, right? But at that pKa, that's the special pH for whatever our given acid is. So they have lists of acids and their pKa's, okay, because those are special pHs. Those are the pHs that they behave like buffers the best at. They behave the best as buffers at those pHs. Okay? This equation here will generally be provided for you. All right? pH equals pKa plus log of, again, A minus here is the dissociated form, and the HA is the associated form. And just a reminder here of how logs work. If I take a solution that has the equivalent amount of A minus and HA, so let's say that I have, under some circumstances, 0.12 molar A minus, and I have 0.12 molar HA, equivalent amount, right? That equals 1. And if I take the log of that 1, that's 0. So the pH will equal the pKa when the concentration of my acid and the concentration of its conjugate base are equal to each other. Which makes sense, because that's what we said. The pKa is a special pH. It's the pH that you'll get when the concentration of the acid and its conjugate base are the same. So again, this equation will generally be provided for you. We just went over here with an ice table how you can identify the concentration, or the pH, knowing the concentration of an acid and its conjugate base with the Ka of that acid. So if you don't want to use the Henderson-Hasselbalch equation, you don't need to, and it will be provided for you. But it can be pretty simple. Not that this is necessarily hard, but the Henderson-Hasselbalch is an equation that from it we learn a lot of other information, so it becomes helpful. All right, so let's see. What's the pH of a buffer made from 0.5 molar HF and 0.2 molar sodium fluoride? Here's the buffer. We're making a buffer. 0.5 molar HF, 0.2 molar sodium fluoride. What is the pH going to be? You want to help me with this one, Brielle? How would you approach it? What would you do?
So I would start by writing out the equation of what would happen.
Okay.
So
HF or F minus? We'd have to use HF if we're going to use this Ka, right?
Yeah. So it's going to be NEF.
HF is going to...
Oh, it's going to go to H and then the F minus.
Very good. Now,
we use our ice table and we're just going to put 0.5 under HF. And then we can use the 0.2 for the F minus. And we can put a 0 under H plus.
okay.
Because of that 0, we know that it's going to move towards the product. So it's going to subtract there and add there, yeah.
Great.
And then we can just finish it by going 0.5 minus x, and then x, and then 0.2 plus x.
Yeah. Sorry about that. There we go. Good. Now what?
Now we fill in our equations, so we'll go the 0.2 plus x. Or do we not need the x?
I think we can drop that, right? We can drop that because we got 10 to the minus 4, and we're at 10 to the minus 1 here, so.
Okay. And then just times x. And then over the 0.5. And then that's equal to the Ka.
All right, fabulous. I'll do this in the calculator here. 6.8 times 10 to the minus 4 times 0.5 divided by 0.2. Oh, what have I done? Divided by 0.2. 0.0017. What does that mean? What's that mean? I got 0.0017. Brielle, any ideas? What do I have to do now?
So that's the concentration of the H ion.
Okay. So what?
Wait, I'm confused. What question am I answering?
What is the pH of a buffer?
Yeah, so wouldn't you just take the negative log of that number?
That's right. Whoops, what did I do? Wrote a question mark? I didn't know you could write a question mark. 0.0017. Okay, so it's saying 2.77 is our pH. Okay, now let's do it the other way. If we're given this equation here, pH equals pKa. How can I get the pKa for this solution? Who is helping? Yeah, Brielle. Help me out with the rest of this. If we're doing it this other way, how can I get the pKa for this problem if I want to fill this equation in? I have the Ka here, right? How can I get the pKa?
Well, I know the pKa is where it's 50% associated and 50% dissociated, but I'm not sure how we get it.
Okay. Well, remember this business? Px equals what? What does Px equal?
Negative log of x.
That's right. Very good. So if I have pKa, that must be the negative log of...
Take the negative log of the Ka to get the pKa?
That's right. Very good.
Okay.
So negative log of my Ka, 6.8 times 10 to the minus 4, 3.16. 3.16. So the pH is going to be 3.16 plus the log of what? Where am I going to get this A minus and this HA concentration?
I know that the A minus is the dissociated form. But what number?
Well, how about the HA? Isn't that this the 0.5?
Yes.
Because that's the associated form, HA, HF, right? So the 0.5 goes down here, and this point, or this A minus, could that be this 0.2?
Yeah.
Yeah, because if I put 0.2 molar sodium fluoride, I'm going to end up with 0.2 molar fluoride ion, which is the conjugate base for this acid, right? Okay, so 0.2 divided by 0.5, and then I take the log of that value, and then I So I've just done this portion, right? And then I take 3.16 and I add it to that value. So that's, again, 2.76. So, very good. We did it two ways. We did it with our ice table over here to the right, and we did it over here with our, what's they're called? Henderson-Hasselbalch equation. And we got the pH essentially identical. Okay. Very good. I think we have some more to practice here. No, that must be it. That's about it. All right, so I think that this is, there's some other stuff here, but because we're kind of out of time, I think this is going to be the last day for, well, we do have to go over those. Yeah, I think we're just going to go over these two things. In fact, we got 3 minutes. I'm going to do it right now because we've already kind of talked about this. In a titration curve, when we plot pH versus the concentration of base, we have our initial point and we have our end point here, our end point. And the point in between is our buffer zone. Exactly halfway in between, we can use that point to identify what the pKa is, right? And this is titrating an acid with a base. If you titrate, this is the titration of acetic acid. If you titrate a strong acid with a strong base, then you'll get a transition here that's very sharp, and it will always pass right through the pH of 7. Because the resulting conjugate base isn't a strong conjugate base, it's a weak conjugate base. And when you titrate something like acetic acid, the resulting transition doesn't occur through 7. Anytime you titrate a weak acid or a weak base, as you reach the equivalence point, you're going to have the resulting conjugate base still around in solution, like the acetate ion. And if it's a conjugate base, that means it's a fairly good, if it's a conjugate base of a weak acid, that means it's a fairly good base. Therefore, it will influence the pH and it will always be above 7. And it will correspond to the concentration of the conjugate base. What do you think, Sarah? I think that you did some of those crazy labs that we did for Chem 105 lab. You know why we're seeing 2 bumps here, like a camel?
No, I'm not super sure.
Okay. Well, this represents the titration of one hydrogen atom on hydrogen ion on phosphoric acid. But then if you continue the titration, a second hydrogen ion comes off of the phosphoric acid. So whenever there's what they call a diprotic acid, there will be 2 bumps like this. And that means it corresponds to 2 pKa's, 2 pHs at which the solution could be buffered with an amount of that acid and its conjugate base, or the different species that are associated with these transitions. Okay, so if we have the last 60 seconds here to kind of just look at some titration curves where we again plot pH versus the concentration of the base that we're adding. Oops, OH minus. Now, it might be a different kind of curve. You might have, in fact, I'm not even going to put that on there. I'm just going to say the reaction occurs this way. If I showed you a titration like this, right, and I compared it to a titration like this, and compared it to a titration like this, and compared it to a titration like this, all right, which one of these, A, B, C, D, which one of these is the titration of a, could be the titration of a a base with an acid. Which one of these could be the titration of a base with an acid? Any ideas, Alyssa?
A titrated base with an acid would make the pH fall because the base would react with the acid, making it less. So the pH going down, so it would have to be C, because you didn't say it was a double reaction.
Yeah, so it could be C or B, right?
Yeah.
Titration of a base with an acid. And these would have to be the titration of some acid that you start with a base. Very good. Which one of these would have to be the titration of a diprotic acid? Which one would have to be the titration of a diprotic acid, Brielle? Any ideas, Brielle, or did you have to get going? Sarah, are you there? Which one of these would be the titration of a diprotic acid?
I think that would be D.
That's right. That's right. Here is a diprotic, meaning there's 2 points where protons come off. It was an acid because it started off at a low pH, so we must have been adding base, right? If this is the titration of an acid, this is the titration of an acid, and then here I'm going to draw a third titration of an acid. Which one would most likely be a strong acid? So this is our E over here. Which one would most likely be the strong acid? It would be E, right? E would be our strong acid. We have a sharp, very sharp transition, and it happens right in the middle. I didn't write any values here, but assuming this is 0 to 14, happens right in the middle. Whereas our weak acids are always going to be slightly basic because of the resulting conjugate base that's around here. Maybe about 8 or 9. Okay. So that's good. That means we're able to stop with our